Okay, so this video will focus on combinations of functions, and primarily we'll walk you through just a lot of different examples so that you're sure that you can apply those combinations in the proper order. So let's begin with one of our parent functions or basic function, the absolute value function, and look at this transformation g of x, which is equal to 3 times the absolute value of x minus 2 minus 4. Now understand, in function notation we could write that as 3 times f of x minus 2 minus 4. So we have three different transformations that are occurring. We have an x minus 2 inside, an outside multiple of 3, and then an outside subtraction of 4. If you recall, the inside addition or subtraction moves the graph left or right, so that means that we're going to move the graph right by 2 units, and then we will apply this factor of 3, so that's going to stretch the graph by a factor of 3, and then we're going to move it down by 4. Now obviously you could use your calculator and put this in, and you're going to have your calculator at your disposal, so I don't want you to get too bogged down in all of this, but I do want you to have an idea. If you had to answer on the test for me, describe the transformation in words, I would want you to be able to do this. So to kind of think about what's going on, we start with the absolute value function, which consists of ordered pairs like negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. Right, we're just taking the absolute value of that x value to get our output. So what this would do, to move right by 2 units, means that we're going to add 2 to the x values, and then the stretch by a factor of 3 multiplies the y values by 3. And then down 4 will subtract 4 from the y values. So if you had to take a point through the transformation, like this negative 2, 2, what you would have to do then is think about where does it go in this transformation. So let me just write it down here. We could take negative 2, 2 through the transformation. To move it right by 2 units would be 0, 2. Then we would have to do what? Multiply the y by 3, so that would be 0, 6, and then subtract 4 from y, so we would get 0, 2. So we would expect that to end up at the point 0, 2. Let's do one more. The 0, 0, which is the vertex of the absolute value, and make sure it follows what we know. So the vertex, we would move it over 2 units to the right to be 2, 0. We would multiply the y values by 3, which would take that to 2, 0. And then we would subtract 4 from the y to be 2, negative 4. Okay? So let's just see what happens when we graph. So I have the graph already drawn here from the calculator just to confirm everything that we hope to be true. So you can see on our graph the vertex is marked. This is 2, negative 4, and then the other point that we have on here should be 0, 2, and that's the point that we have here. Okay, so we've applied the transformations in the correct order to come up with the graph that we need. Now let's look at this next graph of 0.5x plus 1, and let me erase these things here. So negative 0.5x, negative 0.5 times the absolute value of x plus 1. Again, in notation for the function, that could be written as negative 1/2 times f of x plus 1. Okay, so there's no inside change going on. We do have two outside, well actually three outside changes, these factors here. We have a reflection and we have a 1/2, which is going to be a vertical compression, and then we have a shifting up. So the negative on the outside takes the opposite of y. Well, the opposite of y occurs as a reflection across the x-axis, so the first thing that we would have to do is to reflect the graph across the x-axis. And what that really does is takes the opposite of y. The next change is the factor of 1/2. It is a stretch by factor of 1/2, which multiplies the y by 1/2. And then lastly we have a shifting up of 1 unit, which will add 1 to the y value. So let's again kind of take this through some transformations using a couple of these points. So if we start with the -2, 2, and we reflect it across the x-axis, we're going to get that to be -2, -2. Then we have to multiply the y values by 1/2, so that's going to take us to -2. A -1/2 times 2 would be -1. And then lastly, it's going to move up 1 to be -2, 0. And then let's also follow the original vertex through. So the original vertex, when we reflect it, stays at 0, 0. When we take half of the y value, that still stays at 0, 0. And then it should move up to 1 unit, to 0, 1. So let's see, when we take away this, we should have the point -2, 0 and the point 0, 1 on our graph. And you can see those are indeed on our graph. Here's 0, 1 and -2, 0 is here. Okay. So again, the key is to be able to describe the sequence of changes that will take the parent function to this new transformed graph, and for you to have a basic shape, a basic idea of what the shape of this graph looks like. And of course you can plug that into the calculator to confirm, but please be able to describe it verbally. Now here's one where you couldn't use your calculator. So using the graph of f to sketch each graph, and you can go to this other website if you want to print an enlarged copy of the graph. But I'm not going to do all of these. Let's talk about like part D, because A, B, and C are just one transformation only. So D is the opposite of f of x minus 2. Well, here you have to be able to describe what that means to do. Opposite of f times x minus 2, we have an inside and an outside change. Inside change is going to shift it right by 2 units, and shifting right by 2 will add 2 to the x. And then the outside negative, that's taking the opposite of y, which is a reflection across the x-axis. So we're going to take the opposite of y. So when you're given a graph like this, you want to take each point through the transformation. So this point -2, 4, we're first going to shift it to adding 2 to x would be 0, 4. And now taking the opposite of y would be 0, -4. 0, 3 shifts right by 2 to become 2, 3. And then reflecting across the x would become 2, -3. Everybody follow what I'm doing there? 1, 0 takes me to 3, 0, and reflected stays at 3, 0, since the opposite of 0 is 0. And lastly, the point 3, -1, moving right by 2 would be 5, -1, and then reflected would become 5, 1. So let's plot these points and see if we can get the shape. So 0, -4, 2, -3, 3, 0, and 5, 1. Okay. So understand that the shape of this really was rigid, right? All we did was move it around. So that would be the new transformed graph that we need. Just to describe a couple of other things, what happens with f is 1/2 f of x. So that is a vertical shrinking. So basically that's going to multiply all of the y values by 1/2. So the x values would stay the same in that case. The y values get multiplied by 1/2. Now, what about f of 2x? That is one of the inside, the horizontal stretches. When you have a factor there, you're really going to divide the x by that number. So here for f of 2x, what we would have to do is to divide each of the x's by 2 and keep the y. So like -2, 4 would really become -1, 4. 0, 3 would stay 0, 3. 1, 0 would be 1/2, 0. 3, -1 would be 3/2, -1. So that's going to shrink it horizontally. Okay? Now, these are some more where you're describing the transformation and kind of doing what we started out doing. So let's just review a couple more of these to make sure you're pretty comfortable with it. Let's do like 55, because that has a lot of the transformations here. It has g of x is equal to -1/2 times the square root of x plus 3 minus 1. So let's first describe what's going on with that parent function. Our parent function is the square root of x. So to describe the sequence of transformations, inside here, x plus 3 is going to shift the graph left 3 units. So keep in mind what that will do. That's going to subtract 3 from the original x. And then we have this outside -1/2. Well, the opposite outside is going to reflect the graph across the x-axis. Which actually takes the opposite of y. And then the 1/2 is going to be a vertical shrink or compression. It's going to multiply the y values by 1/2. And then lastly, the -1 is going to shift the graph down 1 unit. So you might want to think about what are some original points on the graph of the square root of x. So if we look at our basic function, we know we have the points 0, 0, 1, 1, and we'll choose like 4, the square root of 4 is 2, and so on. So if we move these points through the transformations that occur, 0, 0 would go to -3, 0 first because it's going to move left 3. Then we reflect that point across the x-axis, which would stay on the x-axis at -3, 0. We shrink it down by a factor of 1/2, which 0 is shrunk, stays at 0. And then we move it down 1 unit to be -3, 1. The point 1, 1, left 3 would be -2, 1. Now when we reflect it across the x, that becomes -2, -1. Shrink it by a factor of 1/2, becomes -2, -1/2. And then move that down by 1 unit. So if we subtract 1 from -1/2, we get -3/2. Okay. Let's try one more. 4, 2 shifted left by 3 would be 1, 2. Now we reflect it to be 1, -2. Shrink it by a factor of 1/2 takes us to 1, -1. And now we need to move that down 1 unit to be 1, -2. So let's see if this looks like what we would expect. So if we have now the point -3, 1, -2, -3/2, and 1, -2. So this would look like, oops, sorry about that. That basic square root function that looks like this, okay? And you can confirm that on the graphing calculator. Now, it also says to use function notation to write g in terms of the parent function. So we did that earlier, but that would mean that this is really equal to -1/2 times f of x plus 3 minus 1. Basically, whatever's inside the parent function is inside the function notation, and everything else is on the outside. Okay, and we'll finish up with some that involve a few more of the inside changes, because that's probably the most thing that's new to you, and we're going to use that quite a bit when we get into trig functions. So if I have this function f of x is equal to x cubed minus 4x, and really what I want to do here is just to get your mind thinking about what would the transformation look like, and you can play around with your calculator in doing this. But if I had f of 1/2 x, what does that do to this function? Well, 1/2 x is going to be a horizontal stretch to the graph. What that will do is actually multiply the y values by 2, and the y value, I'm sorry, not y values, I said that wrong, multiply the x values by 2, and the y value stays the same. Okay. And if you want to, you can look at your calculator and see some original points on this graph of f of x. It's a polynomial function, and I'll just write some down here. You'll find things like -3, -15, -2, 0, -1, 3, 0, 0, 1, -3, 2, 0, 3, 15, those are points that are on that original function f. So if we looked at g of x, which is f of 1/2 x, it will multiply the x values by 2, and the y values are going to stay the same. So you would get points like -6, -15, -4, 0, -2, 3, 0, 0, 2, -3, 4, 0, and 6, 15. So it's going to multiply the x values by 2, keep y the same. What about f of -1/2 x? What would that do? Well, the negative on the inside is taking the opposite of x, and the opposite of x is a reflection across the y-axis. So this has both a horizontal stretch and a reflection across the y-axis. And so to obtain points from that original function to the transformed function, you're going to multiply the x values by 2 and then take the opposite. What happens when we reflect across the y, that's where x's are opposite, so then you're going to take the opposite of x as well. Okay? And keep y the same. In other words, -3, -15, if we multiply that by 2, we would get -6, -15, but then we take the opposite of x to get 6, -15. Okay. What about I of x, which is f of 1/2 x minus 4? This one is a little bit tricky because when you have this factor of 1/2 in here, it actually is going to play a role in this constant. We can't just say that this is shifting right by 4. We actually have to apply the 1/2 to that as well. It would actually be shifting right by 8, because we can write this as f of, if we factor out the 1/2, that's really the same thing as dividing by 2, and we would get this in its equivalent form. So what this does is actually shifts right by 8 and does a horizontal stretch. And so we would have to do our horizontal stretch first, which is going to be multiply the x by 2 and then shift right by 8, which would add 8 to the x. Okay, so it's going to be important in which the order in which you perform those two tasks. So the horizontal stretching comes first, and then the shifting would come next. Now what about negative f of 3x plus 1? What would that do to that original function? So we have an inside, the factor of 3 is actually going to shrink it horizontally. We would have a horizontal shrink by a factor of 3. What about the negative on the outside? That's taking the opposite of y, which is reflecting across the x-axis. And then lastly, the plus 1 moves the graph up by 1. So think about the specific things that we do to the original x and y values. We would have to first divide the x by 3, or you can think of it as multiplying by 1/3, whichever way you want to do that. Reflect across the x-axis is going to take the opposite of y, and then up 1 unit will add 1 to the y. So I'm talking about starting with those original points, like the -3, -15, taking it through this transformation. Dividing x by 3 would be -1, -15. Reflecting it would be -1, +15, and then moving it up 1 would be -1, 16. So I want you to kind of think about how you would have to go manually through those transformations. Of course, you could use a calculator. To use your calculator on this, you would enter the original function, x cubed minus 4x. You can actually go through and figure out what this function is, or you can use that vars key, and you can enter negative y1 of 3x plus 1 using the function notation, and that would give you the transformed graph. Okay? So let me know if you have any questions on this. Thanks.